So this is our Advanced Data Tools webcast for October, and the subject today is Informix Storage and RAID5 and how to do storage the right way. Okay, I'm going to be going through the first half very quickly. This is based on a presentation I did at the IIUG conference in 2012 with quite a bit of expansion from new materials that have become available over the last 3 or 4 years. So I want to go through some basics just to make sure everybody's on the same page, and we'll get that out of the way quickly. If you have any questions about that, about any of that stuff, then let me know. Just send a chat to Tom, and when we get down to questions, I can go over anything.
And this is Tom, by the way. I'm actually on his Lester's account, so send them to Lester.
Okay. All right. So you see it. So pull down your chat window and send to Lester's login. Okay. And Tom will give them to me when we do questions at the end. Okay. So let's start. You have various options for the chunks in your Informix instance and for other databases in general. So this is not specific to Informix in any way. One is to use raw devices. Those are the character devices on a Unix system where the privileges start with the letter C. Okay, they represent a disk partition, a logical unit, some other logical or physical partition of your storage with no operating system formatting, no operating system overhead, no caching. Okay, the most important thing to know about raw devices, it is almost always contiguous on disk. Okay, at least within each device. If your raw device represents a LUN on an array, at least within each device, the space is contiguous. Okay. Cooked devices are the same physical devices as the raw devices, but they're marked as block devices. The Unix privileges start with a B. Okay, they're exactly the same physical storage as the raw device, but they do go through the operating system. Okay, there's no file system overhead, but there is some caching going on. Okay. And then file system files. So using a normal file, in other words, as a chunk or a table space for your database. Typically, it's non-contiguous space. At least you have no control over the contiguousness of the contents of the file. The file system governs that, and we'll talk about that in a little bit. And there's some overhead from the file system. Operating system caching is normally active. We'll discuss that. Okay, and the file system structures themselves have to be maintained, right? The file exists within a folder or a directory structure, and that hierarchy has to be maintained. And information about the file, when it was last opened, when it was last modified, etc., all has to be maintained. And different file systems have different requirements, right? Under the hood, the drives can be physical spindles or they can be solid-state drives. Okay, the thing to keep in mind about solid-state drives is that they're only recently getting to the point where their reliability is sufficient for serious business use. They've been around for maybe 10 years, but only in the last 3 or 4 years have they been good enough, in my opinion anyway, for real serious business use. The reliability hopefully will keep improving over time. But the drive lifespan right now is about the same as a spindle, about 4 to 5 years. They will last about the same length of time as your older disk drives did. Okay, and keep in mind that performance varies very widely. Some SSD drives are optimized for writing, some are optimized for reading, some are optimized for an even balance between them. They're all made from different kinds of flash memory, so their performance characteristics from one brand to another, and even within a brand from one product line to another, will vary greatly. So you need to find the drives that do what you need them to do for your operation. Okay. So those drives can have flash in them, they can have DRAM in them, they can have hybrid storage with some combination of flash and DRAM, perhaps using flash as a cache internally for the DRAM as a cache for the flash. Okay, Flash is very fast for read, but slow for writing. DRAM is very fast for writing, but read times may not be as good. Keep in mind for flash memory, writing to the flash decreases the lifespan of the flash. So the more you use your flash drives, your SSD drives, the faster they're going to wear out, just like a spindle, okay, and more so. Okay, there are different kinds of memory. One of the things to keep in mind is that NAND Flash becomes more difficult to read over time if it's not rewritten. So many of the drive manufacturers under the hood will rewrite sectors of the drive constantly in the background to refresh the charge levels on the NAND storage, and that will shorten the life of the storage. Okay, something to keep in mind. Without being refreshed, the storage, the signal and on the NAND degrades over a period of about 8 to 40 weeks, so less than a year. Okay. Another odd thing about flash is that flash memory performs better when it gets hotter. It performs best at around 115 degrees Fahrenheit, which is too hot for most of your computer equipment. Your drive controllers in particular perform much better at lower temperatures, which is why all of your data centers are air conditioned. And SSD controllers, because they don't perform well when they get hot, will throttle down the I/O throughput that they're producing to keep their own heat down, and that will negate the advantage of the flash chips starting to speed up as they get hotter. And data centers, as we just said, are cold places. So flash and SSD drives and data centers are not the greatest match. Something to keep in mind. Okay. On the other hand, Advanced Data Tools did some testing with SSD drives several years ago on Informix 11.7 and 11.5 with our 2010 and 2011 benchmarks. Both performed about three times faster with SSD drives than they did with equivalent spindles. So they are faster with all of the caveats in mind. Okay. Something to keep in mind about Informix. Before Informix 11.10, when you opened a cooked device or a cooked file, a file system file chunk, the file had to be opened with OSync in synchronous mode. And that meant that every write, the engine had to wait for the physical write to go to the operating system cache, and then the cache to be flushed out to disk before that system call returned to Informix, and it could know that the data was safely on disk. And that's very slow. And it's one of the reasons why we always recommended raw disk in the past. Okay. Synchronous writes are slow, as I said, and so file systems, even cooked devices, are 10 or 15% slower than raw devices in general. File system chunks are another 15 or 25% slower than raw. Okay. But as of 11.10 and all the newer versions of Informix, we do have ODirect. You can turn that on in your on-config file. And once you turn on Direct IO or O_direct, the performance of cooked files improves till it's about 5% slower than raw disk. Okay, so the big performance gain from raw is not there anymore. There is still a performance gain. It's just not as significant as it was in the past. All right. And if you're running on AIX in 1150, IBM added support for Concurrent IO, which is needed to make JFS2 file systems perform well. Without the O_CIO or Concurrent IO support, JFS file systems are still about 15% slower than raw. With it, it improves to about 3 or 5%, somewhere in there. Okay. There are many different flavors of file systems: normal file systems that are called lightweight, and journaling file systems, which are all the rage. Okay. Informix pre-allocates chunks so that fragmentation within the initial chunk is going to depend on the state of the file system that you're allocating the chunk from, if you're using file system chunks. Okay. Informix tries to make the chunk contiguous by writing to every page in a file system chunk. If you allocate a raw chunk or a cooked device chunk, it actually only writes to the first few and last few pages to make sure that the storage is big enough to hold the chunk you've defined. But if you define a file system chunk, it will write to every single page so that the operating system will try to allocate as contiguous a space as it has available, okay? But if you mark your chunk expandable, when Informix expands the chunk, you have no idea whether that new piece will be even close to contiguous with the existing pieces of the chunk. Now, that's no worse than creating a new chunk instead, since that may not be contiguous either. But it is something to keep in mind. Okay. You do have no control over the layout of the disk storage within the chunk, okay, within the file system, and that's up to the file system. Okay, and we'll talk about that in a little bit. Normal file systems, right, usual Unix-style file systems from the past, the Ext2 or other Unix-style file systems from the past, that's our baseline for how we examine the performance of other file systems. Okay, there have been some what are called lightweight file systems. They've all been optimized for file type I/O, like opening and closing small files. Okay, databases don't open and close files very often. They typically open a file when they start up, and they leave those files open forever. So there's very little performance gain from lightweight file systems, in my experience, and most database vendors don't have any particular recommendation to use them. Okay. Journaling file systems. Journaling file systems add a form of logging to the file system similar to the Informix, in some cases similar to Informix's logical logs, in order to reduce recovery time and limit data loss if the system crashes while there's unwritten data in the cache. Okay. It also tends to avoid the requirement in Unix to periodically scan the file systems for damage and repair them. Okay. And that's the main reason why system administrators have fallen in love with journal file systems. Okay. There are many different kinds: JFS, JFS2, ZFS, Ext3 and Ext4, Btrfs, XFS. And let's talk about some of them in real quick. So JFS or JFS2 is an IBM invention. It's open source. It's available on Linux and several other operating systems besides AIX. It's the basic operating system file system for AIX. It is a metadata-only journal, so it does not journal file contents, only the metadata. It does serialize writes in order to maintain data consistency, which is why you need Concurrent IO enabled so that the database can update the metadata in parallel. Okay, otherwise that metadata update gets serialized, and that slows things down. JFS is capable of extending a file using variable length extents. Okay, so it builds large files out of bits and pieces, some of which are big, some of which are small, versus other file systems that tend to use fixed size extents. Okay, and it maps those extents to the inodes using a B-tree index, which can improve access times for large fragmented files. Hopefully your database chunks are not fragmented in the first place, so that doesn't become an issue. Okay. Also, JFS locks the allocation groups, which are how it keeps track of free space on the file system, and that means that when it allocates a new extent to a file, and that means that expansion of multiple files at the same time can block each other and single thread, and even contiguous I/O does not get us past that. Okay, so that's one downside of JFS. But again, if you keep your chunks, your database chunks on a separate file system from all of your other storage, that should not become an issue at runtime. Okay, it is a fairly low overhead and fairly safe file system for databases as journaling file systems go. ZFS was developed by Sun for Solaris. It's now open source, and obviously it's an Oracle product. But it uses copy on write transaction model. That means that when you update a page on disk, a location on disk, the data is not overwritten, but a new block gets allocated, the new data is written to the new location, and then the metadata is patched up to point that page or block to the new location, and the old location eventually gets put onto the free list in the background to be reused. Okay, what that means is that your chunks, if they're allocated on a ZFS file system, will become fragmented more and more and more over time. And the most non-contiguous portions of your database will be those that are most active, and therefore the ones you need to be most contiguous. Doesn't make a whole lot of sense. Okay, so I don't recommend ZFS for databases. In particular, the IDS database pages are much smaller than ZFS pages. And that means that if you rewrite the same ZFS page by writing multiple Informix pages, that ZFS page may get relocated many, many times, causing the chunk to become badly fragmented over the disk. Okay. Also, as I said, those old copies of the blocks get cleaned up in the background. That requires a lot of I/O bandwidth and can fight your database for head positioning as ZFS tries to clean things up in the background. Okay. Also, ZFS maintains 2 to 3 checksums for every data and metadata block that's modified, and they have to be modified up and down the tree, the file system tree. So when you change a 4th level directory, its parent directory, grandparent, and great-grandparent directories all have to be updated. So there's a lot of overhead to ZFS. It is, though, a fairly safe journal file system. Okay. Ext3 and Ext4 are the newer Linux file systems that replaced Ext2. They journal both data and metadata. Okay. They are copy on write, similar to ZFS, and that causes your files to become less contiguous and more fragmented over time. Okay. Ext4, by the way, has write-back enabled, and as far as I know, there's no way to disable it. Ext3 write-back is optional. If you turn on write-back or use Ext4, Ext4 writes the metadata entry for a moved page before it writes the data block. And that means if your system crashes between the time the metadata got written out and the new data block got written out, you've got metadata that points to an empty page or garbage. Okay. Linus Torvald says whoever came up with that idea was a moron. I agree. So Ext4 is not safe for your data. You should not have your data on Ext4. The overhead of Ext3 and Ext4 journaling is not insignificant. I would say use Ext3 but disable the journaling. And it's a decent file system. Basically, it behaves like an extendable Ext2, and it's very fast. Also, Ext4 does not schedule dirty page writes out to disk except every 2 minutes. Ext3 does it every 5 seconds, which is a whole lot safer for your data. Okay. The newest Linux file system is Btrfs, or Btree file system. It's still under development, but the disk format is stable as of 2014. So if you have a kernel that was built after 2014, you can use Btrfs safely without worrying that your file system will become incompatible if you upgrade the Linux version. It is copy on write, it is journaled, it has index directories, it has a lot of neat features. It has built-in RAID 0, 1, RAID 10. They are experimenting with RAID 5 and 6. Why, I don't know. It does a whole lot of neat things. I have no idea how it performs for databases. It's just too new, and I haven't done any testing on it. But I thought I would bring it up. Okay. XFS is metadata journaling only. It does write the journal before writing the data, so that there is some risk. Okay, but since the data is not journaled, it actually may increase the risk. But the general opinion is that it's a fairly safe kind of file system. Okay. Okay, so now we get to the good stuff, talking about RAID levels. So RAIDs originally stood for redundant arrays of inexpensive disks. When disks got cheap, somebody changed that to redundant arrays of independent disks. It was proposed, the idea was proposed in a paper in 1988 at SIGMOD because disk drives were too expensive at the time for mirroring to be practical for very large installations, and drives were not getting big enough, fast enough to handle data growth. on a single drive, or even a single pair of mirrored drives. So there were two goals to RAID. One was to allow for larger logical storage, and the other was to increase safety over a single drive without the cost of mirroring. What I'd like to propose, and we'll go through this and tell you and see why, is that today, with the cost of storage going down as quickly as it is, mirroring makes sense again, and then we no longer should be talking about RAID levels like RAID 5. But let's go through it. Okay. Just to get on the same page again, RAID 0 means striping only. We take N drives and we attach them together logically, and we spread our data across all of the drives so that we're always writing to more than one spindle, we're always reading from more than one spindle, and we can store more data on a logical disk drive than could be stored on a single physical drive. Okay. Mirroring means we copy a drive. We have two drives that are connected, and they are copies of each other. Everything gets written to one drive also gets written to its mirror. And you can read from either side of the mirror, and you get the same data back. In fact, most RAID 1 systems can read from both drives in different sectors from both drives in parallel, so that you can actually get twice the read throughput as you can from a single drive, certainly for short bursts. Okay. There are two different combinations of RAID 0 and RAID 1 that are possible. One is to create two stripe sets and mirror them together. Okay, that's come to be called RAID 01, based on a suggestion I made back in 1990, because it got too confusing when every RAID company used different terminology for RAID 01 and RAID 10. So at some point I said, let's all use the same idea. And somebody took my advice. So RAID 10 means we stripe two drives together to make a mirror set, and we take multiple mirror sets and we stripe them together. I'm sorry, we mirror two drives together, pairs of drives, and we stripe them all together to make a larger stripe set. Okay, and that's RAID 10. Okay. So RAID 5 means we take one extra drive in the array and we allow for parity blocks, and we rotate the parity around the drive so that block 1 of the stripe set has parity on drive number 5, let's say. Block 2 has parity on drive 1, block 3 has parity on drive 2, block 4 has parity on drive 3, et cetera, et cetera, et cetera. Okay, and we keep rotating around like that. And what that means is that if we lose one drive, if an entire drive gets lost, the missing sectors that are data on that drive and not parity can be recalculated from the data on the remaining drives and the parity that's on the remaining drives. And we can recreate a missing drive or a crashed drive. Okay, and that was the idea of it, was we get some redundancy without the cost of doubling the number of drives the way you have to for RAID 1 or RAID 10. Okay. RAID 6, somebody came up with the idea that because of some of the problems with RAID 5, which we will talk about, they would add a second parity drive and have two parity blocks. They would all continue to rotate, so you'd have parity on drives 5 and 6, and then 6 and 1, and then 1 and 2, and then 2 and 3, et cetera, all the way around. Okay. Somebody also liked the idea of the way ZFS did things with copy on write, and said if we did copy on write and we built it into an array, we'd overcome some of the problems with what we call silent disk corruption. Okay, and we'll talk about that also in a little bit. And that's RAID Z. Okay, it's basically a ZFS file system built into an array of drives. Okay. Somebody else came up with the brilliant idea that if one parity drive wasn't enough to save us from crashing our data, then we should just mirror the whole array and create two RAID 5 arrays and mirror them together, and that would solve the whole problem. Of course, that means we're using more drives than RAID 10 and getting no additional value from it. We might as well just use RAID 10. And then there's RAID 61, which is just even stupider. I'm just going to go right out and say this, both dumb ideas. Okay. The following points from now on, this is all recognized by the storage industry. This isn't stuff I made up. Okay, I pulled it all. You'll see the link at the bottom of the page to a wiki page that talks about some of these things. There'll also be links to other studies as we go along. So, according to Wiki, The possibility of a second drive failure during recovery is 4 times more likely than the statistics would predict. And the safety of RAID5 is predicated on drive failure rate being very low and unlikely, okay? And keep in mind, those server-grade drives that you spent a fortune on have exactly the same failure rates as the consumer-grade drives that you can buy at Staples. Exactly the same. Okay, so just in case you didn't get this, let me make this point again. The possibility of a second drive failure during recovery is 4 times more likely than in practice. One study I read said that the possibility of losing a second drive from a RAID5 array or any drive array in the first hour after the first drive fails was 20%. And the probability of losing a drive over the course of 2 hours was about 25%. So, okay, keep in mind if you lose a second drive from a RAID5 array, all of your data is lost if you haven't finished rebuilding the missing drive. And I guarantee you it takes more than an hour to rebuild a terabyte drive or a 2 terabyte drive or a 3 terabyte drive. Okay. Atomic rights to multiple drives in an array are not guaranteed. You've got 5 drives or 6 drives or 20 drives or 30 drives in your RAID5 array. There is no guarantee that they're all going to get written at the same time. They're not spindle synced like a RAID 2 or a RAID 3 or a RAID 4 array is, which is one of the reasons why RAID 5 is more popular, because you can read different locations from the different drives, and then so read performance is much better than RAID 2, RAID 3, and RAID 4. And that's why RAID 5 is popular, and RAIDs 2, 3, and 4 died a long time ago. Okay. And because those spindles are not synchronized, the writes are not synchronized, it is possible for your array to crash before all the data gets written for an updated block. Okay. And you're now dependent on your non-volatile cache in the storage array to not lose your data before it can get flushed out to disk. Okay. The following: larger drives take longer to rebuild. That increases the risk of losing a second drive, right? In a recent study, drives over 1 terabyte were determined to be statistically likely to suffer from multiple bit dropouts. Okay, multiple bit dropouts means the drive itself cannot recover the data using its parity. And that means that you're dependent on the RAID parity. RAID parity also can only recover a certain number of missing bits. Okay. So drives bigger than 1 terabyte are absolutely at risk for total failure and total data loss. SSD flash units suffer from bit rot and cosmic ray damage, just like magnetic disks do. Okay, and if they're written too frequently, they suffer from bit rot more so than magnetic disk. The error rates observed by a CERN study that we're going to talk about in a few minutes on silent corruption showed that the actual bit rate was not the predicted 10 to the 16th or 10 to the 17th bits, the way what the drive manufacturers report, but they were observing error rates of 1 in 10 to the 7th bits, or about 1 in every 10 million bits, or about 1.2 megabytes. So if you have a drive with a terabyte of data on it, okay, you have you're likely to lose 800 times the number of bits than is predicted. Okay, it's a lot of data that's at risk to multiple bit failure. Okay, Wiki says these are the weaknesses of RAID5. Okay, correlated failures. In practices, the drives of a RAID array that are all the same age and are all similarly used, right? You installed all your drives at the same time when you bought your array, except for the ones that you've replaced already, and they're stored in the same environment, they live under the same temperatures, they've all experienced the same load, okay? That means they're all likely to fail at the same time. Not only that, most drive failures are due to mechanical issues, okay? more likely than becoming old, is that the drives fail because of mechanical issues. One study showed that 20% of installed drives fail within the first month, 15% within the first month and 20% within the first year. Okay, and that's because of mechanical failure in the drive. And that violates the assumptions of independent, identical rates of failure among the drives. The failures are, in fact, statistically correlated. If one drive fails, there's a really good chance that a second drive is going to fail really soon. Okay, and that increases your possibility of total data loss if you're running a RAID5 array. Okay. Unrecoverable read errors, or UREs. This is a fact. This is because all drives, all magnetic drives, and even all SSD drives lose data over time. Okay, that's why all of your drives have reserved sectors that are used for replacing failed sectors. As a sector gets flaky and the error rate on it, the recoverable error rate on it increases at some point, it gets to the point where the drive decides it will soon be unrecoverable, and it moves that data to a new sector. That, of course, does two things. Number one, now your disk that was contiguous is no longer contiguous, and number two, eventually you run out of replacement sectors because there are only so many of them. There's a small percentage of the drive that's set aside for replacement sectors. Eventually you run out. Those replacements, those sector moves, are not reported to the controller, and they're not reported to the operating system, so your fan does not know that its disks are slowly dying. Okay. And if you, at some point, if those sectors can no longer be moved, they will start to return garbage, because they will no longer be, the error rates or errors will no longer be recoverable, and they'll start to return garbage. If that garbage was not read back to the operating system, so that, let's say, Informix can check its own checksum and see that the page was bad, but is used to rebuild a RAID5, another RAID5 drive that failed, right? Drive 1 fails, drive 2 has garbage on it because of UREs. You now rebuild drive 1, you're rebuilding it with garbage. Now you have 2 drives with garbage on them. Okay. Double protection parity schemes such as RAID6 attempt to get around that issue and the issue of losing a second drive, okay, by adding a second parity drive. However, that increases the write penalty, costs you more every time you have to write, right, because you have to write that many more drives, okay? And it has a much higher risk now of UREs. It doubles the possibility of garbage propagating from one URE to another drive. RAID 10 and RAID 1 do not suffer from that problem because data is never copied from one drive to the other, from one side of the mirror to the other side of the mirror. It's written to both sides independently. Okay. Another thing is, as drives get bigger, it takes longer to rebuild them. We already mentioned this, okay? And even though the individual drives' mean time between failure have gotten better over time, that increase has not kept pace with the increased storage capacity. And so while drives are living longer, it's also taking longer to rebuild one that fails, and therefore we've increased the probability of a second failure over time, okay? There was a study by NetApp, one of the storage vendors, that said the chance of failure increases by 3,800 relative to RAID 5 if you go to RAID 6. That you are more likely to have a failure under RAID 6 than RAID 5, okay, even because of the probabilities that are involved, okay. And they predicted by 2019 the performance on RAID 6 would be as bad. The failure rate on RAID 6 would be as bad as it was in 2010 for RAID 5. Okay. RAID 10 has a bounded recovery time. In other words, you fail a single drive, you only need the time to recover and rewrite a single drive. It's not the time to read several drives, calculate parity, and then rewrite a drive. Okay. Atomicity, we talked about the possibility called the RAID 5 write hole, where one of the drives are not written before the system crashes, and you get garbage. Okay, talked about that. Reliability of write-back caches. There is a concern about write-back caches being reliable. They're supposed to be a non-volatile medium, but they're not. And keep in mind, all of your SANs are write-back cache systems, so they are all at risk. Okay. We talked about UREs. The predicted URE error rate is 110 times 10 to the 14th, or it was a few years ago. It's now probably up to about 10 to the 16th, but as we said, CERN says they didn't see better than 10 to the 7th. Even so, at 10 to the 14th, that's about 12 terabytes. Okay, so if your array is bigger than 12 terabytes, and whose aren't, then the possibility of losing bits significantly enough to lose data, okay, is statistically probable, not possible. So I mentioned CERN. CERN is the European Council for Nuclear Research. The initials are in French, so they'll look backwards. Scientists at CERN were beating the hell out of 1.5 petabyte of data to do research, and they were all stored on RAID5. And they noticed they were getting back garbage every once in a while. So they started to figure out what was going on and why their data was getting corrupted. And this is what the report said. The RAID controllers don't check parity. Duh, I've been saying that for 20 years. When reading data from a RAID5 system, in principle, the RAID controller should report problems to the disk, on the disk level to the operating system. This seems not always to be the case. Actually, it's never the case. RAID controllers do not report parity errors. Okay, do not check parity on read, rather, only on write. So CERN began to do testing. There's a link up on top here that you can follow to get to this report and see what they did. And they said, we wrote a program that writes a 2 gigabyte file containing special bit patterns. And then we read the file back and we compared the patterns. The program was deployed on 3,000 machines and run every 2 hours for 5 weeks. During those 5 weeks of running on 3,000 nodes, they revealed 500 errors on 100 of those nodes, okay? An average of 5 unrecoverable errors on 100 nodes in just 5 weeks, okay? Not years, 5 weeks. 80% of the errors they found were traced to disk firmware that was buggy, okay? Disk and controller firmware that was buggy. 10% of the errors they were able to trace to memory cards that were incompatible with the system boards. Somebody put together their machines with the wrong memory cards. Okay. RAID5, though, could not correct any of those errors, and the remaining 10% they were able to track down to bit rot, either partial media failure or cosmic ray damage. They did say cosmic ray damage. I'm not crazy. And note, CERN is underground. If the cosmic rays got them, cosmic rays are going to get you too. Dell wrote in 2009, RAID5 is no longer recommended for any critical business information on any type of drive. Note, Dell just bought EMC. I don't know what they're going to do about all those RAID5 systems that EMC is installing. Hey, maybe they'll just change their tune and pretend they never said it. So why use RAID 10 or RAID 1? I'll tell you. Number one, it's safer from bit rot because we never copy data from one drive to the other, so you can't propagate garbage from one drive to another, okay? At least 75% less susceptible to data loss from a second drive failure from RAID 10, right? If you have a RAID 10 array that has 5 pairs of drives, okay, or let's say 4 pairs of drives to keep to the 75%, all right, to 4 pairs of drives, and one of the drives fails, if a second drive fails, as long as it doesn't fail on the opposite side of the mirror and it's the same drive, it's the mirror to the drive that already failed, you're okay. All right? So you've got a possibility of any of four other drives failing, actually any of 7 other drives failing. 6 out of those 7 could fail without you losing any data at all. Okay, versus RAID 5 where you lose any second drive and you're done, okay? Also, recovery time on a RAID 10 array is 80% faster than a RAID 5 array, okay? And that further reduces the risk of getting a second drive fail while you're recovering. Performance during recovery only degrades about 10% during recovery. Okay, if you have a 5-pair array, it's about 6.25%. If you have a 4-pair array, it's about 10%. The more drives you have in your RAID 10 array, the less total performance degrades because read performance is only degraded when you're reading from the one pair that is in the process of recovering. All the other pairs are running at 100%, okay, full speed. Versus RAID5, where every drive is involved in recovering the missing drive. And so your performance is about 80% slower. On a RAID 10 array, your read performance will be as much as 200% higher than a RAID 5 array during peak loads. Okay, CERN's report validated this, and all of my testing has always validated that, because RAID 10 can read from both sides of the mirror different sectors from the same drive, same logical drive. Write performance is sustainably 100% faster than RAID 5 without adding any huge and expensive cache memory to the SAN. Yes, we had to add more drives. Drives are a whole lot less expensive than cache memory. Keep that in mind, especially today. Wasn't true in 1988. It is true in 2015. Mirroring each drive from a different drive lot reduces the danger of hardware and firmware bugs causing data corruption on your drives. It also reduces the possibility that a second drive from the same hardware lot failing and within a short time after the first drive failure will cause you to lose any data, because the mirror drive will have been made from a different hardware lot, and therefore less likely to fail. Okay. Any questions so far?
I'm going to chime in. There was one question from a little bit ago coming in asking about AIX and specifically the direct IO. If on AIX with 11.5 using raw disks, you don't need, and this would be most cases raw disks, you do not need to enable direct IO in the on config, correct?
Correct. Direct IO has no effect on raw disk, and it has no effect on cooked devices, on block devices either. It only takes effect for file system chunks. So it doesn't matter whether you enable it or not. It's not going to do anything.
Great. That's the only question I've gotten in so far.
Okay. Okay. The only reason to enable direct IO if you primarily use raw disk chunks would be to have it configured and ready to go if you happen to have to add a file system chunk in an emergency until you can get more drives added to your system, or if you happen to use, well, that wouldn't take effect either. I was thinking about temp space, but temp space doesn't go through asynchronous IO anyway. So that's a different story. That doesn't go through synchronous IO anyway. All right. Any other questions?
That's. Is there any actual protection against cosmic ray damage?
No, except for turning your building into a Faraday cage. There really isn't. I mean, it's a random thing. You know, your drives could go for years without getting any cosmic ray damage, but you could get it. And like as I said, CERN did see things that they could attribute to cosmic ray damage. So it is a possibility. You know, it's low on the list. You're more likely to hit a URE than cosmic ray damage. A URE from fading sectors. Also keep in mind, if your drives are older than 4 years, if you have drives that are more than 4 or 5 years old, it is time to replace them before they start to go, and they are going. I guarantee it. Drives last roughly 4 to 5 years. That's about it. Any drives that are older than that, you will be calling me to recover your system. I'm recovering a hospital system right now. I was doing it earlier today. I'll be doing it this afternoon because their system got old and the drives crashed. They lost all their data, and their backups are also partly corrupted. So, all right, replace your drives before they get old.
You generally say a 3 to 4 year cycle on that?
I would say, yeah, 3 to 4 year cycle for replacing drives. 4 years tops. Drives that are older than 5 years are already have most of their replacement sectors used up. They're on the verge of unrecoverable errors. You want to get there before that.
Also just want to check, because we normally do you have any problem sharing the presentation on the website when the YouTube goes up for this?
No, it'll go up. The presentation materials will go up with the recording. All right. I think I just saw a question pop, but I didn't catch it. No. Was there another question?
That's what I've got right now. One other thing I will actually interject from my experience as well. If you're running on CookSpace on Ext2 or Ext3, there's a parameter you can pass to, the fstab or wherever you're actually calling the mount from called no A time. That'll actually prevent the file system layer from constantly updating the write time on files, and that can actually have a small but measurable improvement to your performance when running on Cooked.
True. One of the comments I've got when I recommend people to use Ext2 rather than Ext3 or Ext4 is that you can't expand an Ext2 file system while it's mounted. You have to unmount it to expand it. So, but keep in mind you can create you can mount an Ext3 file system without journaling, and that's just as good. And then you can expand the file system while it's mounted. So Ext3 with journaling disabled has the same performance characteristics as Ext2. Same with Ext4. Though honestly, I don't know if you can actually disable the journaling on Ext4.
I have not found a way, but there's some deep stuff that you can actually tune in the kernel that you might be able to do there.
Yeah, don't know. Not a kernel guy. All right.
All right. I've got a couple of announcements, but I didn't know if you had more you wanted to go through, Art.
Nope. I'm just gonna let me slide while you're talking. Let me slip through the closing slides.
Okay, great.
All right.
Couple of announcements. If you've not listened into our webcast before, after the fact, it'll take a few days. We transcode we take the whole video, we put it up on YouTube, so it'll be freely available there. So if you want to review it or go back through anything, it'll be up there. Just check our website. I think Lester said it would be probably closer to the end of this week or even this weekend before he's going to get a chance to get that posted. But we'll post it up there. There'll also be a copy of the slides, so all this is freely available. We have a couple of announcements on Informix stuff. The Informix User Group Conference 2016 has been announced May 4th through May 8th. This is going to be in Ponte Verde, California. It's going to be right near the Sawgrass Marriott Golf Resort. The base website's up, iug2016.org. There will be more information posted soon. The other one is if you are in the Washington, D.C. area, Virginia, Maryland, Delaware, Pennsylvania, on November 17th, we're having a WAG meeting. It's going to be from 8:30 till noon or early afternoon. We're going to be covering Genero, ER and Grid, and going over some of the future technologies that work with Informix. So this is a free meeting in Tysons Corner, Virginia. WAG.org for more information. So are there any other questions that anyone has? If you want to send a chat, you can, of course, Art has his information in here, and we're all reachable at Advanced Data Tools. If there's any follow-up questions you'd like to, have, or any general thoughts on the presentation, we are always welcome, welcome back, any feedback you want to give us. We're, as we have here, as Art's put up, we're figuring out our next couple of presentations for December and January. So we will be announcing those fairly soon for what the topics and what the dates will be. We've got a few things that we're currently finishing up.
Okay. Also, if you're going to be at the IBM Insight Conference next week, Lester and Tom and Mike and I will all be there, so look for us. Tom and I will be around Monday and Tuesday anyway at various Informix sessions, and the others will be around all week. So.
Also, Mike Walker has a really good one on Informix with Internet of Things on Wednesday morning.
All right. Thank you all.
All right. Thank you, everybody, for being on. Again, this will be posted up in a few days, and look forward to our having you on the next call.